A marketing trick, almost as old as marketing itself, is to create a solution and then convince consumers that they have a problem. It has a long and storied tradition. From RCA Select-O-Vision, trademark, to the Tapwave Zodiac, trademark, it always produces success, or, at the very least, a very memorable failure. Now, nVidia is stepping up to the plate with its new line of graphics cards, the RTX series, which promises to deliver a new generation of increased graphical fidelity with Real Time Raytracing. And just like the aforementioned products, RTX is both a technological achievement and something whose ideas will likely become popular 4 or 5 years down the line. nVidia also uses the equally old tactic of bullshit marketing speak and acronyms. RTX's precursor, GTX, stood for, and I am not making this up, GeForce Technology Extreme. So, in this video, I'm going to explain what ray tracing even is, why it's important, and why nVidia's implementation of it is so lackluster. Sadly for mathematicians everywhere, the real world doesn't operate on pixels, textures, and simple math. It instead operates on photons and molecules. So, of course, the best way to generate realistic images is to just simulate the processes in the real world that lead to vision. That of photons emanating from light sources and bouncing into your eyes. The problem is that if we just simulate every single photon from every single light source, we are massively wasting our time and computational power. If only less than 1% of the photons actually reaches our eyes or the camera, why bother simulating the rest? So instead, ray tracing works in reverse. For every pixel on the virtual camera, we fire out a ray, which we then simulate in reverse. Think of looking at a mirror. Rather than photons emanating from light sources and bouncing into your eyes, we trace the ray in reverse and work out how bright it should be. We then work out the amount of red, green, and blue light in this ray, and voila! We have our pixel. But just simulating one photon per pixel leads to graininess and unrealism we don't experience in real life. Why? Because of outliers. Let's take a look at this texture of asphalt. Overall, the asphalt is relatively matte, unreflective, and dark. But inside of this texture, there are spots that are far brighter and far darker. And when we render with this limited resolution of 1 photon per pixel, the color of these spots is not the average color of the area of the pixel, but is instead the color of one specific point in that spot. This doesn't happen in your eyes or on a real-world camera, because both capture billions of photons, and in the case of the eye, the detail is too small, and in the case of the camera, that pixel is actually the average of all the photons that hit it. So we actually need to simulate multiple photons per pixel. The amount of photons we send per pixel is represented in 3D modeling programs such as Blender as samples. The more samples, the less grainy the image. The image starts to look good at around 64 samples, say. So let's actually do the math. Let's say we want to render at 640 by 480, a very low resolution now, but perfectly fine back when Milli Vanilli were still popular. Okay, so that's 307,200 pixels. And let's render at, say, 64 samples per pixel. That's 19,660,800 photons to simulate for every single frame. That's a lot. And each photon isn't even super simple to calculate, especially if we have fog, clouds, or human skin in the image. This super simple shot of literally just a concrete cube on wood took 15 seconds to render on a system considerably more powerful than what most people are playing on. And if we introduce fog and more lights, the render time quickly skyrockets. First to 34 seconds with fog, and then when we add 3 more lights, it bumps up to 43 seconds. Sure, it looks brilliant, but what use is that if we have to wait around a minute per frame? So instead, we approximate this process using math, and a lot of it. Rather than working out the path of every photon per frame, we can just figure out how certain surfaces in general respond to light, and run that considerably faster calculation instead. This method is called rasterization, and every image you see in any modern 3D game, be it a masterpiece like Kerbal Space Program or Call of Duty 532, is rendered like this. The thing is, these equations are not perfect, and their quality varies pretty drastically depending on the material. We have rocks and some types of less reflective metal down pretty much perfectly, but the approximation for human skin is rather more, what is that thing? Get it away from me! Human skin is not just a simple matte surface, but is instead semi-transparent. And worse, whatever is under that skin influences its tone and color. That's what makes Caucasian skin peach. Black skin, however, absorbs more light, and not only lets less light reflect back, but also less light pass through. This feature of skin is called subsurface scattering, and right now we have two options to approximate it in real life. One, it looks terrifying and like plastic, or two, it looks slightly less terrifying and less like plastic, but it drastically lowers frame rate. Rasterizer engines also struggle on mirrors, or reflective surfaces. After all, there are no photons, so in order to get reflections, the engine either has to render double by creating a second camera for the mirror, or the developers can generate a pre-rendered reflection map beforehand, which not only is more effort, but it's also not dynamic, meaning it does not change if the environment changes. Ray tracing, on the other hand, has these and all other features of materials in real life built in, including all the imperfections and all the edge cases. So in order to create materials, all you need to do is write the code that describes them as they are in real life. So if RTX can live up to its promise of bringing ray tracing to games, it can have both massive graphics and gameplay consequences, both for the player and for the dev. But how does RTX manage to achieve ray tracing in real time when even the highest end hardware from when it was released struggles? Spoiler, it doesn't. Before we get to the bad, let's talk about the good. How does nVidia manage to achieve ray tracing at all? The answer is some clever engineering that requires you to know a little bit about computers. All processors, including graphics cards, are built around something called an architecture, which describes the layout of the transistors in that chip. For CPUs, such as those made by Intel or AMD, these architectures have to be compatible with a broad variety of applications and be able to execute difficult limited compute tasks. So their design generally has less cores and less ability for multitasking, and more power per core. Graphics cards, on the other hand, don't really focus on big, monolithic compute tasks. Instead, they work on generating an image on screen. And each individual pixel is not that hard to calculate, most of the time at least. So rather than having a few powerful cores, they instead have thousands of tiny weak cores, each calculating a couple of pixels per frame. This enables them to be specialized for both rendering images, and it also makes them much, much better than traditional CPUs at certain applications. So a GPU has far more cores and far less power per core. But rather than doing either of those, nVidia crammed additional tensor cores and ray tracing cores onto the chip, which are specialized for AI and ray tracing respectively. So the design of a ray tracing core is a bit different than either CPUs or GPUs. They have a number of cores somewhere between a CPU and a GPU, about halfway, that also run incredibly fast and have plenty of power for ray tracing. So this is how nVidia managed to get ray tracing working in real time at all. But even with these specialized cores, true ray tracing in real time is still far away. So what did nVidia do? Well, the answer is somewhat disappointing. Rather than ray tracing the full scene, nVidia ray traces around 1/10 of it and feeds the results back into a more traditional rasterizer engine, enabling it to have greater detail. This means that compared to actual ray tracing, RTX on can be a tad disappointing. And it also means that RTX games lack the most exciting feature of actual ray tracing, that of perfect, accurate graphical simulation. And even with this cut-down version of ray tracing, the performance is not perfect. The entire rest of the scene has to wait for the ray tracing to finish before doing anything else. So turning on RTX can make the FPS of a scene drop precipitously from around 100 to 30. However, these RTX cores can be put to actual good use in programs with actual ray tracing, like Blender, where their ray tracing acceleration can be taken advantage of, halving render times on occasion. So, in conclusion, ray tracing is an amazing technique that can drastically improve graphical fidelity by simulating the real world. But RTX doesn't do it. In fact, it seems to be very, very good at almost every single task except what it was actually designed for: real-time ray tracing in games.